Record. Yes. All right. Today's class is purely online. The video recording will be available as usual right after the class. And today we continue talking about classical machine learning models. So the main topic for today is support vector machines. Yes. Before I begin, a couple of logistical notes concerning seminars. So very soon, within 1 week, I will release the set of papers and um, well, you have to select the groups and as well as the rules for grading and assessment for the seminars. This year, just still being verbal, I want to say that you have to read the papers, prepare a presentation presented during the assigned days. And in turn, you also have to attend some other seminars. The reporting type would be an electronic quiz. Well, it won't be a quiz in terms of answering to given tasks. It will be rather free-form quiz where you will summarize the seminars which you have attended. And for me, this will be the means for assessing you in this course moment. Do you have any questions regarding this? Right. Soon I will release the rules in textbook, so it will become clear. Yes. Last time we started to talk about fundamentals of machine learning, and today we go into a more advanced topic. And before that, I want to spend some time on kind of summarizing the preliminaries so that we are all on the same page. First and foremost, so we are talking about the case of building models based on collected data points, collected observations, and these observations are variables through which we observe a specific phenomenon, or in other words, features. So, sure. So x1, x2, xn. So so it can be like temperature, pressure, whatever. And you use these variables to sample environment. Through your sensory system. For convenience, or for kind of more formal treatment of this case, we will talk about vector of features, or feature vector. Where essentially we talk about a vector in many dimensional space where the number of dimensionality is equal to the number of your variables. So we denote it as bold letter. And so we have x1, x2, x, and so in this form we talk about vector data. Uh, Right. And the basic model, learning model that we can use in uh, for classification purposes. So our task is essentially to separate, or not even to separate, to decide where a given sample. So if we have this many-dimensional space, so let's have a three-dimensional space with values for feature 1, feature 2, feature 3, and you have set of observations. And somehow these observations are known to belong to different categories. And so now you have a new observation. Use another symbol. And you want to decide to which of the known categories it belongs to. And probably the most straightforward way of doing that is to check the distances. So now we are talking about geometric interpretation of the problem. So we have multidimensional space. And we want to check distances. So let me just a moment. From a given sample to some known points. Right? And decide so basically to which category it belongs to, depending on the distance. So here we have several alternatives, several options for us. The first one is to use the difference in coordinates for all the features. So and sum them up. So if you have sum for all features. And what you do, you take the value, well, of so you have your sample D of feature I. X1, D is data here. And minus D X. Two. So you have 2 points Sorry, I think I messed it up a little bit. So let's call it point D1, and this one is point D2. I messed up the indices. D1, D2, and you take corresponding coordinates, and just to be sure that you're positive, so you take a modulus. And in this case, we are talking about measuring a Manhattan distance or L1 distance. So there are different other alternatives, obviously. So what you can think about, you can take sum of D1 I minus D2 I square and the square root of it. So and in this case, and this is also for all the features. And the square root should be obviously be outside the sum. So in this case, we have Euclidean distance. L2 distance. In general, so the distance can be defined. So, distance can be defined as sum over data between any 2 points, data 1 minus data 2 for corresponding coordinate to the power of p and 1 over p. So in this way, we are talking about Minkowski distance. So I mean, where you vary p, and this distance measure will capture different aspects of your data. So this is Minkowski distance. So now I want to maybe stop talking and ask you. So these different distances for different p's, what kind of aspects they capture, and in terms of relative difference between the values of each coordinate of a vector. Please feel free to unmute.
Could you repeat the question?
Yeah, so what is the difference between different distance measures? So whether you have 1 here, so Manhattan distance, or 2 Euclidean, or 3, etc., etc. So what can you say about it?
I guess that, for example, if the Manhattan distance is based in the absolute values, it's more prone to outliers, and when you apply a square or a square root, you are smoothing those outliers.
Exactly, and the larger is p, the more it actually sensible to outliers. For a very large P, so it captures um, the differences in the individual features, the magnitude in the individual features. So if you have, for example, one feature with very large magnitude, so as you said, Euclidean distance smoothes out this over all population of features, and the higher SP, the more sensitive it is to individual outliers. Another measure of distance, or rather similarity, which is used in machine learning, are dot product and cosine similarity. By the way, am I? Ah, yes, I'm sharing the screen. Yes, sorry. Similarity measure. So similarity measure, well, an obvious difference from distances is that it focuses on the angles between vectors. So if we have two features, x1, x2, and we have two data points, so or four data points, and those are our vectors. So distance is obviously the measure that captures this quantity. Another way of taking a decision on belongingness to one category or another would be based on angles between the two vectors. So alpha. So for example, if we have here one vector of the same category, so here we have alpha 1, alpha 2. And two measures that capture this are a dot product, where you basically sum up so in our notation, so these are data points. So data point point 1 coordinate I multiplied by data point 2 coordinate I. So this is the definition of dot product. So sum of pairwise products of coordinates of vector. What you connected to this measure is a cosine similarity. Which is basically dot product divided by the norm of the vectors, the product of the norm. So d1 multiplied by norm of d. So that is the difference. As the name suggests, it captures the similarity between two vectors. So if angle alpha 1 is smaller than alpha 2, this means that, and this was our, say, d1, and this one is d2. 2. then D1 is more similar. D1, D2, D3. So D1 is more similar to D2 than to D3. Than D3. Okay. But the important point, so later on we will see during today's class is the usage of this measure of similarity so that you can recognize it. Another point. Maybe on this note, I want to remind you the following. That the following holds. So if you have a dot product between two vectors, so the following holds. So if you have dot product, so normally, let me just write dot between two collinear vectors, so vector which is in the same point to the same direction. So you have A, A. So this equals to norm. So just remember this for future discussion. Yes. On the same note, so let's remember some school stuff. So preliminaries. So if we want to define a line, so now we have X and Y axis here. Or no, let me use this X1, X2. And we want to define a line, so which is on some offset beta from the origin, and also is inclined by the angle alpha. So one of the forms to define this line is x2 equals to alpha x1 plus beta. Well, this is just one of the ways. There is a canonical representation, which for a 2D case looks like this. So you have a1 coefficient x1 plus a2 x2 plus b equals 0. So this is a parametric definition of the line. Or in other words, we can write it in the following way. I x I plus b or if the in the vector form, so we can write like this. Again, so this is on the rights of notations. Another thing to remember for today's discussion is the way how to compute a distance of a point to a line. So if you have some original coordinate system with your features or coordinates, and first of all, now we can draw a line. But now the question is, so if you have a point on this line, point P, with coordinates x1, x1, 0, x2, 0. So how to calculate this distance to a line? So you draw a perpendicular line and you want to calculate this distance. So again, not going into the details. Again, there are different ways how to derive this distance. One of the ways to choose a point on this line and build own coordinate system, and so calculate the distance to this chosen point, and then you solve the and then you apply Pythagoras. But so the long story short is that this distance is now calculated as follows. So you have this sum of no, I'm sorry. So just I will write it for 2D case. Then you can obviously generalize, so not to mess up with the indices. So you have your first coefficient a1, x1, 0, plus a2, x2, 0, plus b, absolute value, and divided by a1 square plus a2 square. So this is the formula. So depending on where you look at, I mean, look up for this formula, so you may see different notations for the coefficients, but so the idea is basically this. This we will be using for building our vector machines. And last part of preliminary, so that concerns solving optimization problems. Again, then very, very briefly, I want to give you the idea. So about optimization. Using Lagrangian multipliers. So here, again, so at this moment, I just want to remain on a very abstract level. So you have a function f. Uh, you want to minimize it. F, given certain constraints. So, for example, what can be a function to minimize? So, that could be, for example, f equals 2 plus x squared plus 2y squared, such that x plus y equals 1. So this is your constraint. And constraints are denoted as g. So this is your g. So in essence, you construct the following formula. So Lagrangian. So which is a function of both the original function and the constraints. So so of x and alpha, which is f minus some coefficients and your constraint function. So this is g. So what you do now, you can take derivative of the Lagrangian with respect to the original variable, so the x, and the alphas, so the coefficients in front of your constraint. And to minimize the whole to solve the minimization problem, so you make this partial derivatives equal to 0, and you basically understand. Solving these equations, you compute the values for alpha, which minimizes this function. All right, so far so good. So let's yeah.
Sorry, can you repeat what was the distance calculated in the upper part, right?
Well, you mean here?
Yeah.
So this is a distance from a point. So from some point in this coordinate system of two features, I mean, just to visualize, to a line which is specified by a certain parametric equation. So you draw a line, so you can describe this line in this way. So now your task is to compute the distance from this point to the line. I should probably remove this arrow to confuse you. So this is a line. So far it's a kind of maybe abstract, but problem, but that's what we are computing here, and this is the equation. So this A1, A2, those are the coefficients of the parametric form of the line equation that defines this line. and x1 naught and x2 naught are the values of the features x1 and x2, and b is a free coefficient.
Okay, thank you.
So compare it to what I started this class with. Deciding on the category to which a given data point belongs to uh, when knowing some data samples. We can now approach solving this problem slightly differently, because um, this first alternative is not very optimal by many means. For starters, so there is no kind of generalization there. So it's a pure memory-based learning. So you have your data points stored somewhere in your memory, and you basically in this way, using some distance measure, you implement the nearest neighbor classifier. Here, we're now entering into a model-based classification, which is an alternative approach, which is based on building a model that allows, which when computed, this model, it gives you an answer to which category a data sample belongs to. So, so you have a model, um, well, call it a function in a general sense. It can be a distributed function, as we will learn later on uh, with artificial neural networks. It takes a data, it takes a feature vector as an input. Some maybe previously unseen, and it outputs it spits out the result. So category category 1, for example. And I deliberately chose to go deeper into support vector machines, because it gives this very intuitive view on how model-based classification or many model-based classifiers work. And this view is based on geometry of data. Geometry. And again, so we will start. I make most of the introductory reasoning based on very simple case where we have two features only, and we have only two categories. So or in other words, binary classification. And this means that we have a positive class and a negative class. And here, I mean, so now we become quite some formal. So it's not just positive in terms of correct, not correct, and negative kind of meaning incorrect. But we give it a mathematical interpretation. So our class labels, they can be really either positive, take either positive or negative values. So +1 or -1. So this is for positive, positive class, and this is for negative. So, and I put negative in quotes and positive in quotes just to see the difference. So here we talk about numerical labels, which are either positive ones or negative ones, and we give it a meaning that labels which are positive ones, so they we call them positive class, and negative ones for negative class. Yes. Okay. And what does it mean then? Yeah, graphically. So we have two classes. Our two classes. So first we have our two features. Not necessarily that. Well, it's very easily extendable to many more features. X1, X2. And then we have points, the data samples. And again, so they, for example, arranged in some manner in this space of features. And we say that somehow all these samples, they should be mapped to +1 Y label. And all this circle data, they should map to -1 Y label. So, and we are about now building a model that takes a data point, a vector of features x1 and x2, and produces either +1 or -1. And again, so the easiest, the simplest case to for the reasoning is a linear classification. It means that our model is actually a line which can be defined in this very way. So now we will take a break, 5 minutes break, and after that we will dive deeper into SVM implementation. 5 minute break. We resume 10 to 2. In the meantime, if you have questions, please unmute and talk.